So in this video, we're going to go into more of the details of the different reactions we've covered so far. So we're going to be talking about leaving groups, nucleophiles, and solvent effects, and how they affect the rates of reactions of SN1 and SN2 reactions in particular. So first, we're going to look at leaving groups. And for all these subjects, the book goes into a lot more detail than I'm going to be covering here. I'm going to be covering kind of just the basics of these things, and not going into a ton of detail, but I'd highly recommend looking at the book for some of these subjects as it goes into a bit more detail and gives you more substance to sort of chew on. So, right, like we've talked about before, leaving groups are the group that leave in a reaction. And so the more stable a leaving group is as a free species, meaning there's no negative charge or very delocalized negative charge, the faster it will leave. So in general, what that means is that leaving groups in substitution reactions are weak bases. So what I mean by that is, right, looking at the list of halogens here, right, iodine is a much better leaving group than fluorine, right, because as we remember from our acid-base discussions, iodine, right, is a much larger atom than fluorine, so it has that very delocalized negative charge due to size. Right, iodine is much bigger, that negative charge is much more spread out, so it is a better leaving group. Right, and that is totally correlated with the fact that it is also a weak base. Right, because remember that hydroiodic acid is a stronger acid than hydrofluoric acid, and so the conjugate base forms of them, right, a stronger acid has a weaker conjugate base. Right, so we can say better leaving group. And so, right, inversely, right, groups that are too basic to be a good leaving group are some of the following. Right, so if we try turning these into good leaving groups, or if we try turning these into leaving groups, right, we'd end up with these very harsh, essentially strong bases, right, with these negative charges on atoms that don't really have anywhere to go. Right, the negative charge is very much on that atom and not anywhere else. So we know that these are not good leaving groups, right? So how do we get them to be good leaving groups? So something we can do, as sort of described down here, is we can transform them into a good leaving group using acid-base conditions. So the approach to doing that is as follows. I'll zoom in here a little bit. We essentially turn, right, in this case, the alcohol into a protonated species, right? And again, water here is just here for a solvent. But essentially what we see now is we have that sort of hydronium ion now, right? This positively charged, essentially water species. Right, so if we wanted to make this a good leaving group, now we have. And so the next step for this would be, right, because we have a tertiary carbon, right, and water, as mentioned before, is our solvent, this is going to be our leaving group, right? So this will be a SN1, right, an SN1 reaction. And to that we have a really great leaving group now is water, right, because it has, as we've discussed before, no negative charge, right, so that makes it a really good leaving group. And of course the last step of this reaction would be just that SN1 substitution to that carbocation to get our final product. But this is the process, right, of going from a weak or really poor leaving group, right, OH minus, to a really good leaving group, which is now water. So we're now discussing nucleophiles, right, and we've mentioned this before, right, we talked about the rates of reactions. With SN1 reactions, a nucleophile has no impact on the rate of reaction, right, because it only depends on the concentration of the electrophile. And for SN2 reactions, nucleophiles have a huge impact on the rate of reaction, right, because they depend on the concentration of both the nucleophile and electrophile. And so when we're thinking about nucleophiles, we have to think about the strength of the nucleophile. And in general, what we'll see is that the strength of nucleophile parallels basicity. So a better base means a better nucleophile. And what's important to note here, and we'll talk about this in a little bit, is that not all good bases are good nucleophiles because they can deprotonate, right, in an acid-base reaction faster than they'll react as a nucleophile, leading to an acid-base reaction rather than substitution. So we'll talk about that in a second, but in general, a stronger nucleophile means a stronger base. So there's three very general rules that we'll look at. So one, if nucleophiles are from the same row of the periodic table, strength increases in the same way as a base. Right, so what do we mean by that? If you remember from talking about acid-base reactions, we know that when you go from left to right on a periodic table, you have a stronger acid, right? And so what that means is the stronger acid you have, the weaker base you have. Right, so we're looking at this first example here when we have water and ammonia, right, we know that oxygen, right, is further to the right. The nitrogen, right, is more electronegative. So H2O is a stronger acid than ammonia, right, because oxygen is more electronegative, it's happy to take that negative charge, more so the nitrogen, which is not as electronegative. So what that means, inversely, when we look at the conjugate base, is that, right, NH3 is a stronger base, and therefore a stronger nucleophile. Right, H2O is a weaker base and a weaker nucleophile. Right, because we can look at their conjugate bases and determine, yeah, OH minus, right, is a weaker base than NH2 minus. And so when we're looking at the same type of atom, right, as we see here, we can say something very similar, where, right, with just methanol here, it is a weaker nucleophile than C3O minus, right, and that comes right from the strength of nucleophile parallels basicity, right, because we know this will essentially just be the same arrow, where we have a stronger bases right to the right here, and so they're stronger nucleophiles. Right, because we know, right, OH minus, or, right, our CH3O minus, because these negative charges, they're stronger bases than their counterparts to the left, where they are neutral. Right, these are not as good of a base as these are, because these are very ready to take a hydrogen, right, a proton, in order to get neutral, but these, right, water and methanol are happy as they are. And in the middle here, sort of the condensed formula, but the reason why this molecule is in the middle, if you haven't already guessed, is because of resonance. Right, so this negative charge is delocalized, so it's not as harsh of a base as, right, OH minus, but it does still have a negative charge, so it is more basic than, right, methanol or water. And so next up, when we look at the nucleophilic strength increasing down a column, right, in the periodic table, not stable, we find that the nucleophilic strength increases, right? And so why is that? Right, because if we think about it, right, we know that iodine is a weaker base than fluorine, right? Fluorine should be a stronger base because HF is not as acidic as HI, so the conjugate base should be stronger, right? So we already know that something is not as similar as it was before, right? These are weaker bases, but they're stronger nucleophiles. And so why is that? And the reason for that comes from the polarizability of the electrons. Because if you have, right, a much larger atom, right, that's approaching a electrophile to do an SN2 reaction, right, a really small, harsh negative sphere, right, that valence electron sphere, is going to have a harder time doing the SN2 reaction, but a much larger sphere, something like iodine, would be able to insert into that sp3 backlobe of the carbon much easier. Right, so that's kind of the reason for it. But in general, right, without thinking too much of the semantics behind everything, when you have nucleophiles going down a column, the strength increases, and if you're looking at nucleophiles from the same row of the table, the strength increases from left to right. That's all you kind of need to know for this part. So for number 3, steric bulk decreases nucleophilicity. Right, so we're looking at these two bases, right? They might look pretty similar, right? They're both O minuses, there's no resonance going on. So why is this tert butoxide much more or much weaker of nucleophile than OH minus? Right, so we know this is a stronger nucleophile, and this is a weaker nucleophile. And it kind of comes down to, again, as it says, is this steric bulk. Right, so if you have this molecule trying to do, for example, an SN2 reaction, right, you have these 3 really big methyl groups. So this molecule is going to have a hard time doing a backside attack. All right, so steric bulk makes it difficult to do a backside attack. So you'll often see these sort of species instead acting as a base. Instead. Because the species can take off a proton a lot easier, right? Because hydrogen's very small, right? Rather than act as a nucleophile. And we'll see some examples of that in a little bit. So finally, we'll talk about solvent effects. And in general, again, these are very generalized rules. The book, again, goes into more detail with these, but we will take a quick look at some of the different examples of this. So for SN1 reactions, a polar solvent, right, solvent with those dipole moments, stabilizes the carbocation intermediate so it increases the rate, right, it lowers that activation energy. So if we had something like this, where we had, right, our carbocation, that is tertiary, it would be stabilized by, for example, water as our solvent, right, so there's tons and tons of water molecules in here, and so we would be seeing a lot of stabilization going on, right, with that partially negative oxygen. Right, so this would stabilize, right, that carbocation intermediate. So it lowers the activation energy and makes the reaction happen faster. Conversely, if we have an SN2 with a negatively charged nucleophile, right, you can imagine a polar solvent, because it stabilizes the negatively charged nucleophile, right? So for example, if we had, say, OH minus, and then we had a bunch of water molecules, right, in solution, right, with those protons being partially positive, it would end up stabilizing that negative charge and making it weaker, right, making it less reactive. So this decreases the rate. An SN2 with a neutral nucleophile, the polar solvent will stabilize the transition state, very similar to up here, what we showed with the carbocation. The polar solvent will stabilize the transition state and lower the activation energy. So in general, what we see here is when we have an SN1 reaction, the solvents typically used are called polar protic solvents, meaning it is a solvent that can hydrogen bond. Right? We have all these oxygens attached to a hydrogen, right, which we know is good for hydrogen bonding. So in general, we'll have something looking like this for our solvent. And for SN2 solvents, it's something called polar aprotic solvent. And by aprotic, we mean without hydrogens attached to the electronegative atom, in most cases oxygen. Right, so each of these molecules are still polar, right? We can see they have a dipole moment, but there's no longer any chance for hydrogen bonding. So for SN2 reactions, we'll see solvents like this, DMF, acetone, or DMSO, as the solvent underneath that reaction arrow. And this will help clue you in on what type of reaction it is, if you have to predict the products or do a mechanism. If you see these polar protic solvents, typically it'll be an SN1 reaction, and if you see these solvents below the reaction arrow, it'll typically be an SN2 reaction. So when we meet in lecture, we'll go ahead and go through these two different examples, one where we determine which nucleophile is faster, and then the other where we determine what type of substitution is occurring and which solvent would go best with it.